All right, kids, so let's finish up this in case you missed my last um, lecture. All right, ionic bonding. Hopefully not my last lecture. The bonding that occurs between a metal and a non-metal, and we always told you it was ionic, and I'm trying to make some sense out of what happens here. That happens due to the fact that the non-metal will remove the electron from the metal, and the result will be a positive cation from the metal and a negative anion from the nonmetal, and then plus and minus attract, and they'll come together. So that is similar to, not that one, but this one. Let's go this way. So what happens is, hopefully you realize at this point that for a positive and negative thing to come together, it doesn't take any work. I pushed that a little close, and now they're coming together because of their attraction. So pluses and minuses attract one another. And if we have metals on one side of the periodic table and nonmetals on the other side of the periodic table, the reason that they bond together in this ionic fashion, in this sort of hostile takeover of an electron, is because if you think about the electronegativities of metals versus nonmetals, you should see, let's see what that is, electronegativity wise, most of the metals are very low and most of the nonmetals are very high. So in the fight for an additional electron, if an electron is out there for something to go grab, these anions, these nonmetals, will go after it to become anions rather, and these metals will often just let it go to whoever is around. So sodium and chlorine. Now sodium is bigger than chlorine because it has more of a shielding phenomenon happening on its one electron. So even though they're in the same group, group 3, sodium is a little bigger than chlorine. But what happens is chlorine, with its larger electronegativity, has a desire for more electrons, and sodium, with a very low electronegativity, doesn't really care. So the electron leaves sodium and goes to chlorine. And here's the key. Here's the kicker. Sodium, as a result of that, gets smaller, and chlorine, as a result of that, gets bigger. So let's see that again. An electron leaves sodium, goes to chlorine, sodium gets smaller, and chlorine gets bigger. And we're going to want to discuss that here in a minute. The other kind, the non-metal, or even metal with a metal, has more of a sharing of electron phenomenon. And that's due to the fact that their electronegativities are close. So on one metal with another metal, we'll have very close, like if we had iron and nickel or iron and copper, right? They have very close electronegativities. They're going to want electrons similarly, as will nonmetals and nonmetals. And hydrogen sort of falls in this nonmetal situation. 2.1, it wants electrons, so it wants to be over here with carbon and such, but they will have such a small difference in electronegativity that they will share an electron. It may not always be fair, but they're going to share. So to show you what a shared electron looks like, that's all covalent bonding. So here's a hydrogen atom. It's one proton and one electron. Here's another hydrogen atom. They have an equal desire for electrons, and when they come together, they basically share each other's electrons, and that makes the bond. That's a covalent bond between hydrogens. And it's kind of like they're holding hands, but in reality what they're trying to do is wrestle it from each other. But since each one has the same pull as the other, because they're both hydrogen, they can't really do that, and it just sort of stays in the middle like that. And it's a bond. It's a covalent bond. They're kind of stuck together. I guess I can't try to pull them apart. Maybe I can. Nope. All right, so we'll play with that when we get back from break. So sharing electrons, you can have multiple ways of sharing. There can be sort of an equal share, which we call nonpolar. There can be an unequal share, where they're quote unquote sharing this teddy bear, but this kid really has it more than that kid. And there's also just this hostile takeover, like we just saw, which is ionic, where basically one has complete possession over the electrons and the other one doesn't. So these are variations of the same phenomenon of how much are electrons being pulled away. And it all boils down to this electronegativity difference. The bigger the difference, the more one atom can pull away an electron from another. If it's a small difference, say here and here, like nitrogen and chlorine, right? There's no difference between those. So neither one is really going to pull it more than the other. So that would be more of an equal share when the electronegativity difference It's similar. Unequal share if it's favoring one over the other, and a complete takeover when the difference is so vast that the electron moves. And we say that ballpark, that line is 1.8. If the difference between electronegativities is 1.8, we say that hostile takeover takes place. It's unequal if it's 1.7 to like 0.5, and it's more equal if it's 0.4 to 0. But understand, for us to say that 1.8 is where the hostile takeover happens and 1.7 isn't, that's basically like saying this electron in a 1.7 situation is spending all but 2 weekends with one atom, right, of a year. Whereas in the 1.8, it's not spending any weekends of the year. So it's a very thin line, really. It's a gray area. It's much more of a spectrum from sharing to no sharing at all. And just like here, you can see it's a yellow color up here and it's a blue color down here. And where that blue starts and the yellow ends is a little bit up for debate. Does it really happen here or there, or, and it's the same with this polarity or this sharing situation. Is it a hostile takeover at 1.8? That's just what I say. That's sort of what's been accepted in polarity difference, but it's not necessarily true. Another way to look at this is if a tadpole, right? Here's a tadpole, here's a frog. At what point is a tadpole no longer a frog? And we could argue about when it happens, but the reality is this is definitely a frog. That is definitely more like a fishy tadpole. And at some point in between here, it turns over from tadpole to frog. And so too, at some point, does equal sharing become a hostile takeover? At what exact moment does it happen? It's hard to say, but we kind of say it's at 1.8 electronegativity difference. All right. So the point about the radius getting smaller, if you'd look at something like calcium, which has 20 protons, 20 electrons, if it were to lose 2 electrons to become calcium 2 plus, now it has 20 protons pulling in on 18 electrons. So there's actually more than a 1-to-1 ratio of protons to electrons. And because it has a greater than 1-to-1 ratio, it can pull those electrons in closer. Not to mention the fact that by losing these 2 outer electrons, it now only has 1, 2, 3 energy levels instead of 4, right? Here it's 4. And by losing that energy level, it also got a little smaller. So calcium got smaller for 2 reasons. One, it kind of lost that outside energy level. And 2, because now it has more protons than electrons, and it can pull those in tighter. If, however, chlorine, which has 17 protons and 17 electrons, adds an electron to become a nice stable noble gas configuration, the reality is, though, chlorine can't pull those in as well as it could when it was a 1-to-1 ratio of protons to electrons. Now it's electrons, there are more electrons than there are protons. And so because of that, the atom gets a little larger, the radius gets a little larger because the force of attraction for those electrons is decreased from a 1-to-1 ratio to less than a 1-to-1 ratio. And so it gets a little bigger. All right. So even though chlorine minus and argon and calcium all have the same number of electrons, they all have 18 electrons. Calcium is pulling them in tighter because it has 20 protons pulling those 18 electrons in. Argon has 18 electrons being pulled in by 18 protons, so that's sort of in the middle. And then chlorine has 18 electrons being pulled in by 17 protons, so it can't do as well. All right, and here is the summary where you can see things that are positive that lose electrons are smaller than their neutral non-positive atoms. So here's what half of a sodium atom would look like, and here's what half of a sodium ion would look like. Here's what half of a magnesium atom would look like, and here's half of what a magnesium ion would look like. So they get smaller as they lose electrons because it's allowed to get a little more attraction in there. And the opposite happens when they gain electrons. When an atom gains electrons, like sulfur here is a normal sulfur. Here's sulfur with 2 extra electrons. And you can see that's bigger than that. Here's oxygen, neutral oxygen, 8 protons, 8 electrons. Here's oxygen with 10 electrons. 8 protons can't pull them in as well as here, so it's a little bit bigger. So you see when electrons are added, atoms become larger, and when atoms lose electrons, they become smaller. And that is that. Good work. We will have this test tomorrow or whenever it is you want to do it.